So today I'm going to talk to you a little bit about section 2.1. That is entitled the division algorithm. And this is, well, it's kind of a funny choice of words. It is the standard choice of words, but it's a funny thing. Mathematicians refer to the division algorithm, and it's not an algorithm. What they mean is this theorem that goes like this. If you have two numbers, n and d, oh, wait a minute, I better stick with a and b because that's the way they do it in the book. Given integers a and b, with b being a positive one. So a can be positive, negative, 0, but b's got to be positive. The division algorithm really is specifying what happens when you do division. In other words, the thing they call the division algorithm, this theorem, is the result that you know about because of the way division works. So what is the way that works? Well, given the divisor and the number it's divided into, there's a quotient and there's a remainder. And those are uniquely determined. So there are unique integers, q and r, and how does that work? Well, if you divide a by b, you get q, but then there's a remainder of r. Let me write this on the side a second. A over b is equal to q plus the remainder divided by b. But the way the division algorithm is actually written is smarter than this, because everything here in this statement is an integer so far. But if you do something in a computation like this one, where there's division in it, you're not necessarily in the world of integers. So if you just clear the fractions, multiply through by b, you get the statement that they use in the division algorithm, and then there'll be no fractions. It says a will be equal to q times b plus r. That's almost the whole story, but there's one other thing, which is this wouldn't be unique unless you really have r the proper size, so that you know how a remainder works. The remainder is something smaller than the number you're dividing by, because if you had a remainder that was bigger than that, you could still take away one more copy of b and make q go up by 1. Anyway, so the extra proviso is that r is the right size, as I put it. 0 less than or equal to r less than b. r has to be strictly less than b. The smallest it can be is 0. Right, so that statement is what we mean by the division algorithm. And I suppose we ought to talk about the actual division algorithm as opposed to the result of the division algorithm, and maybe we'll run an example. So how do you actually run the division algorithm? You start, or you initialize the algorithm with the givens. Given a and b, what we're going to also want to do is set things up properly. So we'll set q equal to 0. And we don't really have to do anything with r, I don't think. We're going to assign r once we get into here, but I guess we could set r equal to 0 as well, just because we're going to set it to the right thing in a minute. Okay, so the first thing out of the gate is you ask yourself, oh, wait a minute, I was about to screw this up, so that's good. Let me not do what I just said. Don't set r equal to 0, cross that out. Set r equal to a. Start it out big, because the first thing I'm going to do is ask you, is r less than 0? Is r less than b? This is the question, is r less than b? If the answer is yes, we'll do one thing, and if the answer is no, we'll do another. And what are those things? Well, if R is less than B, then it's already the right size to be a remainder. Which means if R is less than B, you're done. I don't know how to say that we're done. Maybe put a stop sign. And what are you going to return in that case? Q is 0, or yeah, Q is 0. Q is whatever Q is. Let's just say return Q and R. I was thinking about that the first time through, we would return 0, but we're going to come to this decision question again. Let's think about what we do when R is not smaller than B. Well, we're going to do two things. We're going to bump Q by 1. So Q is going to be equal to Q plus 1. And then we are going to subtract B from R. So that's saying, you know, R wasn't small enough to be a remainder, so we subtract again. This is actually why this spot right here is why this algorithm is called repeated subtraction. We repeatedly subtract B from R, and each time we do that subtraction, we pop the value of Q up by 1 unit. Until eventually, R in fact gets small enough and is smaller than B, in which case we're done. You've probably heard it said before that multiplication is repeated addition. Well, the flip side of that is division, which is what we're trying to accomplish, is repeated subtraction. You just keep track of how many times you need to subtract. All right, so where do we go after we do these things? We go back to this decision box. We ask, now is R less than B? And if it is, we're done, and if it's not, we'll do it again. We'll keep going like that. Eventually, though, since R is getting smaller, and we're gonna eventually arrive at something that's smaller than B, and then we will end. So that's more or less the process. I probably should be a little bit more honest with you. A could have been a negative number, in which case Q is going to end up being negative, and we won't be adding 1, in that case we'll be subtracting 1. It's just easier if you think about this in terms of both A and B being positive, which is what I was just doing. I kind of wanted to sweep that under the rug. But my Boy Scout nature got to me. Anyway, this is not part of our book or part of what you need to know necessarily, because again, the math people call the division algorithm that result I just gave you. That A is equal to QB plus R, and R is smaller than B, so it's remainder sized. Let's actually run the algorithm and come up with an example here. Suppose, I don't know, suppose A was 37 and B was 5. I'll show you a run through this algorithm by making what's known as a trace table. So a trace table is just a table with a column for each of the variables. So we have A and B for sure, but we'll also need Q, and we'll also need R. And then when we initialized everything, A is whatever its value was. Well, let's give it this. It's 37. And B is whatever its value is. Remember, Q was 0, and R got set equal to A, 37. The first time we went through the loop, what we're going to do is ask, is R less than 5? No, it's not. Great. What do we do to it? We subtract 5 from it, and we make Q go 1 bigger. Q becomes 1, and R becomes 32. And actually, A and B never got changed. They're they're always going to be 37s and 5s, so I'm not going to continue to write them. Just imagine they go all the way down the table being the same. The next time through the loop, is r less than 5 yet? No, it's not, so we will bump q up by 1 and we'll bring this down by 5. It gets us to 27. Then 3 and 22. Then 4 and, what is that, 17? 5, 12. Almost there, right? Take away one more 5 from there, bump this up to 6, we're at 7. Oh, so close, right? Where did I go wrong somewhere in here? Because 12 minus 5 is 8, that's why. Am I doing that wrong? No, 12 minus 4 is 8. What? Somewhere along the line I went south. Oh, they go 7, 2, 7, 2, 7, 2. That should be a 7. I can see the digits and the units placed like that. But the next time through, we'll bump this guy up to 7, and this guy gets dropped by 5, it becomes 2. And that's where we stopped, because remember what the question was in the middle of that algorithm. Is r smaller than 5? Now it is, so we end. And that's the numbers we'll return, q and r. If I've gone through this algorithm correctly, then we should be able to say that 37 is equal to 5 times 7, or q times r, q times e would be like that, 7 times 5 plus 2. Does that check? Yeah, 35 plus 2 is 37. Woohoo! So yeah, that's how you actually come up with q and r, but again, the statement of that we call the division algorithm is just the existence of those guys. We want to prove that. And it has a pretty quick standard proof. There's a couple of different variants people use. I think the version in the book is just a little sketchy at one point, but it more or less gets the thing straightened out. The main point of the proof of this is going to be using the well ordering principle. So in order to apply the well ordering principle, you have to have a set that you know for sure is non-empty that's contained in the natural numbers. And let me show you how we'll build that set. Let S be the set that's defined like this. It's expressions that look like A minus KB, where, well, the only restriction on that is K is an integer. So do you want to look at what that looks like in terms of our example? Just on the side here, let's do some scrap paper work on the side. When A was 37 and B was 5, A minus KB is those numbers that you were seeing in the Q column as I was going down the list. There's things like 37, 32, 27, 22. Of course, K there could be an integer, so if K was -1, this would be really adding a B to it, so we'd have 42 above that, and more that way. There's all the ones that come down until you get to the remainder was 2, but there's things below that as well. Negative numbers can come out of that expression. Would it be -3, then -8, and so on. Now that collection of things, S, has got both negative and positive entries, and it goes in both directions towards infinity. So that's kind of a bad set, because you can't use the well ordering principle there. But we can make a new set by intersecting S with the natural numbers. And I mean 0 is a natural number too. So if S happened to contain 0, our set A would contain 0. Now this set only has numbers that are 0 or positive. So it's bounded below, and the well ordering principle holds. And that means this thing, S intersect N, has a least element. I don't know if I'm sorry, just in terms of constructing this proof, I think it might be smarter to not name this set. Just say, consider S intersect N. We don't have to have a name for everything that we write down. We can call it S intersect N. It has a least element by the well-ordering principle. And what do you think we call that? Well, in our example, this would be the least element here because these things would no longer be in it once we intersect it with the naturals. That was the remainder we just got. So call it R. Great. Well then R, this smallest entry here, looks like something minus, it looks like A minus something times B. That is, since R is in an element of S intersect N, in particular, it's in S. And the things that are in S look like that, right? So, there is an integer. That was K up here, but I think I'm going to name it appropriately now. What do you think the name of that integer be? Yeah, that'll be Q. Oh, I'm supposed to say the word integer before I wrote that. Such that, well, what it just says up there, R equals A minus QB. And I hope you can see that you can just solve that for A and get the form we're after, A equals QB plus R. Now, you might think I'm done because I've just discovered what R is and what Q is from this stuff. But there's some subtleties we got to consider. Well, first of all, I haven't done nothing about telling us, making sure that R is small enough. R needs to be the right size to be a remainder, so it has to be smaller than B. That's one thing. Well, let's do that. What's the inequality that we need R to satisfy? I'm going to just erase half of the proof and I'll try to work down from the top. Eventually we're going to need a whole new screen, but I want you to still be able to refer to that bit while we write up above. I want to show that that R is the right size. That's the first thing. We want to show that 0 is less than or equal to R is less than B. And part of this is very clear. That 0 is, that R is at least as big as 0 is really obvious because R is in S intersect N, so in particular it's in N, and the smallest thing in N is 0. I'm trying to force a word in where it can barely fit. It follows that 0 is smaller. Well, I should say it the other way. R is less than or equal to, R is greater than or equal to 0. That's what I want to say. But I need it also to be smaller than B. Well, this is sort of a miniature proof by contradiction. So first I'm just going to say it, R is less than B. Because why not? Because why? Well, if it wasn't, if R was greater than or equal to B, we could still have done one more subtraction, couldn't we? That is, we could make Q one larger and subtract another b out of R. We're sort of, if R was bigger than B, it means like in the algorithm part of this, we stopped one short of being done. We could have taken one more b out of it. All right. My brain was saying non-negative and my hand wrote positive. Actually, come to think of it, we don't even need that modifier. Wow, first I wrote positive, now I wrote non-negative. In fact, it turns out I don't need it at all. So, wow, excuse me for revising as we go. But if R is greater than B, then R cannot be the least entry in our set. What do we call that set? S intersect N? Why not? Because you could subtract one more B from it. Now it's time to clear off the bottom half of this board, and hopefully we can finish with just one more half of a board. Let's check this out. If R is greater than or equal to B, and I subtract B from it, I'll have something, if I imagine taking B away from both sides of that, you'd have R minus B is greater than or equal to 0. But also, R minus B is smaller than R. Let's just write it as an inequality. R minus B is less than R. That's a contradiction. Do you see why? Well, R was supposed to be the smallest thing in that set, and now we found something even smaller that still is positive, or still is non-negative, but is smaller than R. A little weird how to say this. One of my favorite phrases is when you have one of these least things, you'd say it's a minimal element. So we would say it contradicts the minimality of R. How about I'll phrase it awkwardly because it sort of makes sense this way. It contradicts R being the smallest entry. I'm taking one thing for granted, that is that, remember the things in this set here? They were the things of the form A minus KB. And I'm taking for granted that we can see that R minus B looks like something of that form. And it does, it's just a change of what the K is. Maybe that's a detail I'll ask you to fill in. Figure out what K, if R gives you Q, what K would make A minus KB be R minus B? Okay, that's not one of those things that you do as an exercise for the student. Let's just do that on the side so that you see it. If we had R equals A minus KB, sorry, for R this number is Q actually, and we take away B from everything here, so R minus B equals A minus QB minus another B. Well, that means that you can think of that as, there's both of these last two terms have a B in them, so R minus B is equal to A minus Q plus 1 times B. So in other words, we weren't quite done with the division algorithm. We could bump Q up one more unit and reduce the remainder by B units, and then we would get a true thing. Well, you see, that's kind of the point of a proof by contradiction. This whole little sentence right here is just a miniature proof by contradiction that R has to be smaller than B. Because if it wasn't, then we weren't really looking at the smallest thing in that set. Okay, I hope that's clear. So that piece I've done shows that R is the right size to be a remainder. Here's a problem. I've only figured out what R is. Do you know what Q is? Well, actually you do. Once you know what R is, what Q is determined by that. You could imagine solving this expression for Q. If R is known and A is known and B is known, you're going to be able to figure out what Q is. So Q's value follows once you know what R's value is. I think I'll gloss over that. Now here's another issue with what we've done thus far, which you really got to watch for. In the statement of the division algorithm, it said R and Q are uniquely determined integers such that that expression, A equals QB plus R, uniquely determined. That means there's an onus on us to show that there's a uniqueness there, that R and Q couldn't be something else. So how do you show uniqueness? Well, there is actually a very standard approach to showing something's unique. You suppose it wasn't, so again, a miniature proof by contradiction. If it wasn't unique, then what happens? And hopefully you get a contradiction. So let's just say that to show uniqueness, suppose that we had some other Q and R that satisfy the conditions of the remainder of the division algorithm. Quotient remainder theorem is another way people refer to this. And just for simplicity, I'm going to call them Q prime and R prime. I don't mean anything about calculus here. I'm not taking derivatives. I'm just a way to refer to another Q and another R. Suppose that Q prime and R prime satisfy the same relationships. I am going to have to do that same trick of using the bottom half of the board. How far should I go? At least leave that bottom sentence on because we're continuing from there. Okay, show uniqueness. Suppose you had a Q prime and R prime that also satisfy, well, A is equal to Q prime times B plus R prime. And R prime is sized to be a remainder. So R prime lies in between 0 and B. Sorry, R prime. So that's strictly less than B, greater than or equal to 0. Now, this again is in the spirit of a proof by contradiction. So we're looking to figure out how do we reach a contradiction from here. Well, one thing is true. If I'm trying to say two things are determined uniquely, what's interesting here is that if one of them, if Q is equal to Q prime, or if R is equal to R prime, then the other two are going to be equal. So let me just put it in terms of R prime. If R and R prime are equal, then what we've got is that A is equal to Q prime B plus R prime, and A is equal to QB plus R. But these guys are the same, so it means those guys are the same. I better make an English sentence out of this calculation I'm doing. Note that if R equals R prime, then well, let's put this other piece in parentheses. Because what we really want to say is that Q prime B equals QB. that's gonna work, unless b was 0, but we know that b is guaranteed to be a positive number, so it's not going to happen that way. The only way this happens is if q prime and q are equal. Alright, so there's one issue dealt with. If r and r prime are equal, q prime and q are equal. And you could do that vice versa. If the q's were equal to each other, it would turn out the r's would need to be equal to each other too. And it's a similar trick. We're using what do we call the transitive property of equalities, that this expression equal to a and this expression equal to a means these two things are separately equal to one another. And then we're taking off the r and r prime from each side because those things are equal. And then dividing by b, yeah, but so that's just half of it, because what if r and r prime are not equal? Right, so if we're in the scenario where r prime, or r and r prime are not equal, then without loss of generality, you can pick one of them and say it's the bigger of the two. Without loss of generality, r prime is larger than r. Now just let me parenthetically remind you where these things come from. We had a equals qb plus r, but also I keep writing my a's and turning them almost into q's, it's weird. A equals q prime b plus r prime. That's the one with the primes in it, is the one. Okay. So I can subtract one of those from the other, and then I'll get 0 on the left, right? Because it'll be a minus a. So 0 will be equal to, what was I doing? Taking this one minus that one, I believe. Okay, so it'll be qb minus q prime b plus r minus r prime. I'm gonna parenthesize this like so. There's no effect, it's just grouping them so that I can see what happens. This side, this first set of parentheses has a b in it, so we have b times this difference, q minus q prime. And that one I guess I leave it alone, r minus r prime. That's 0. But if you have two things that add up to 0, that means they're negatives of one another. And you can take the negative of a subtraction just by reversing the order. So the conclusion from what I just said is that r prime minus r should be equal to b times q minus q prime. Cool? Well, that just means that this little difference, r prime minus r, is a multiple of b. It's in the set, well, could be 0, but it's a positive multiple of b, isn't it? Could it be b itself? Could it be b or larger? Because in fact, what I think is the case is it has to be 0, which is that these two things are actually equal to each other. So if r prime minus r is equal to b, well, we've got a serious contradiction, because r prime and r are both in the range between 0 and b. Bad kerning. We have a contradiction. Since r and r prime both satisfy the inequality that they're between 0 and b, smaller than b. Well, let's just say what they satisfy together. The smallest either of them can be is 0. We said way back that r prime was bigger than r, so first it'll be r, then it'll be r prime. But a cap on both of them is b, the biggest they can be. Actually, they can't even be equal to b, they can get up to it, but not equal to it. Well, how am I going to have two things that are trapped between 0 and b have a difference that's b? You see that that's contradictory? You might want to think about it on a number line. Here's 0, which is included in our collection. Here's b, which is not really there, it's an open endpoint. And r and r prime are in like here, r and r prime. That difference there is, that's how far apart they are. Could that be b, which is the whole width of this thing? Heck, nothing that's in here differs by b. You'd have to go all the way to the endpoint. So yeah, that's contradictory. Usually, in written works, you say something like, we have a contradiction, but a lot of times on blackboards, people will write two arrowheads butting into one another to indicate a contradictory thing. Well, what's that contradiction do for us? That's what we wanted. It shows that actually r and r prime have to be equal, and q prime have to be equal. Well, wait a second, not quite. What it really shows is that r has to be equal to r prime. But look, if r and r prime are equal, I sort of spoke through this before, you could then use the fact that these two expressions are equal and the things on the right of them are equal to deduce that q and q prime were equal. That I will leave as an exercise for you to think your way through. All right, so that's the division algorithm. Its proof, isn't it surprisingly involved? You really have to get into the details of it before you see how that flows. I'm not sure I'm happy with the way it flowed for me just now, but it's something. Next, we're going to look at another algorithm, and this time I am actually going to show you the algorithm. It's called the Euclidean algorithm. It goes all the way back to Euclid, who may not actually have been a person, but anyway, it's presented in one of the books of there are like 12 books of Euclid. The first 5 are geometry, and then there's a bunch about arithmetic. The Euclidean algorithm shows up in there. So that'll be coming in a second installment. So, bye.